Okay, so this is the last section in chapter 4 that we're going to discuss. It's section 4.9, rank, nullity, and the fundamental matrix spaces. So we're going to begin with a theorem, something that we sort of hinted at in the previous section. The theorem says that for any matrix A, the row space and the column space will have the same dimension. I want to point out that this does not mean that the row space and the column space of a matrix are the same space. They're not. In general, they're not. In fact, if you're dealing with a matrix that's not square, it's impossible for those two spaces to be the same because they're subspaces of different vector spaces. We saw that in the previous section. However, even though the subspaces are typically different, they're going to have the same dimension for any matrix A. So, to see why that's the case, I'm not going to read through this proof line by line. Instead, I'm just going to refer back to kind of something we mentioned in the previous section. The way that you calculate, or the way that you come up with a basis for either the column space or the row space of a matrix A, you always begin by row reducing A until you get its row echelon form. So that's what we're talking about when we talk about R here. This is the row echelon form of A. To find a basis for your column space for A, what you would do is look for any columns in that row echelon form that have a leading 1 and then trace those columns back to the original matrix to find your basis. But you do the same thing to find a basis for the row space of A as well. The row space is going to consist of all of those rows in your row echelon form, or sorry, the basis for your row space is going to consist of all the rows in your row echelon form that have a leading 1 in it. So that actually implies that both your column space and your row space will have bases with the same number of vectors in them, because the number of vectors in either one is equal to the number of leading ones in your row echelon form. So that implies that the dimension of both of those spaces are equal to each other. So that leads into this next part, a couple of terms that we want to define. The rank of a matrix. When we talk about the rank of a matrix, we're referring to the dimension of either its column space or its row space. Because those dimensions are the same, there's no confusion about which one it refers to. It's just that common dimension. Then we have the nullity. The nullity is the dimension of the null space of a matrix A. And we're going to see soon that these two numbers that we have for any matrix A are very conveniently related. So let's start by first finding both the rank and nullity for a given matrix. So in this matrix here, we want to find its rank and nullity. It's a 3 by 5 matrix. And I'm going to start with the rank because that's what we've been talking about for the most part so far. Remember, the rank is just the dimension of either the row or the column space. If I were to row reduce this matrix and put it in row echelon form, or in this case it's in reduced row echelon form, but either one, the rank is just going to be equal to the number of leading ones here, because remember that means I have 2 vectors for my basis for my row space. So this would tell me that the rank of this matrix is 2, just by knowing what those two just by knowing that there's 2 leading ones there. So I say rank of A is equal to 2. But what about the nullity? Well, remember, the nullity is the solution set for this linear system if I were to write AX equals 0. Now I can find that solution set just by creating an augmented matrix out of this, and then again, row reducing. So this is in Gauss. I use Gauss-Jordan to put this in reduced row echelon form. If I was using it as an augmented matrix for a homogeneous linear system, then I would have needed to include these zeros here. Okay, but that leads to a solution set with parameters. So for example, if I were to think of this as x1 through x5, x1, x2, x3, x4, x5. And then if I were to assign parameters, let's say r, s, and t to x3, x4, and x5 respectively, then x1 could be written as, I'd be creating an equation out of this and solving. So it'd be negative 3r plus 4s plus 2t. That's x1 is equal to that. x2 would be equal to 5r minus 5s minus 9t. And then I have x3 equals r, x4 equals s, x5 equals t. So I'm going to move that up so you can see that. Okay. And notice this gives me a way of writing my solution set parametrically. So I could write it, let me do this over here actually. Put that up. I could write my solution set this way. Negative 3r plus 4s plus 2t, that's my x1. My x2 looks like 5r minus 5s minus 9t. Then I have r, s, and t. And as we've done before, I'm going to rewrite this as a linear combination of vectors where the r, s, and t are appearing as the scalars in that linear combination. So if I were to do that, let's start with r. I look in each position for where an r shows up, negative 3r, so that's going to give me a negative 3 there. 5r, I'll get a 5 there. R is by itself, so that's like a 1, and then there's no r in the last two components, so those become zeros. Okay, then plus s. I have a 4s, so that's going to be 4, then negative 5, 0, 1, 0. Plus t times, this will be 2, negative 9, 0, 0, 1. Okay, now this is me representing my solution set, my general solution for my homogeneous linear system as a linear combination of three vectors. And I've mentioned this before, but anytime you do this process, these three vectors are guaranteed to be linearly independent. It always comes out that way. So we're looking at the span of these three vectors, and if these three vectors are also linearly independent, then those three vectors are immediately a basis for my null space. It's a basis for the solution set for this homogeneous linear system, which is what the null space is. So that means I have three vectors in a basis. That would mean the nullity is 3 in this case. And I want to point something out too. If you know that this is going to happen every single time, if you know that the number of vectors here will end up being the dimension of my null space. So I'm going to go ahead and write that actually. Nullity is that dimension, turned out to be 3 in this case. We can arrive at this result a little bit quicker if we just notice that the number of vectors in this general solution correspond to the number of parameters that I came up with for my solution set. But the number of parameters that I come up with in my solution set is the same as the number of free variables that the system has. So the nullity is the same as the number of free variables in this system of equations. Similarly, if you notice the rank, we got it by looking at these leading ones. The number of leading ones in this linear system was 2. And remember, every column in this matrix corresponds to a variable. Each one of those variables is either a leading variable or a free variable. So what that kind of points us towards is this really interesting result, which says that the rank of a matrix plus the nullity of a matrix, of that same matrix, is always equal to the number of columns in that matrix. And you can verify that here. 2 plus 3 was 5, the number of columns in this matrix. That result is commonly called the Dimension Theorem, which I talk about here. Actually, let me point one thing out before that, though. I did mention up here the column space of A would be a subspace of Rm, row space is a subspace of Rn, and rank is the common dimension between those two. So this is actually kind of an important fact as well. The rank of a matrix, if you haven't determined what the rank is yet, we know a maximum possible value for the rank of the matrix. It has to be at the very most the smaller of these two numbers, m or n, where those are the dimensions of that matrix. And again, that's because if the rank of A is that common dimension of your column and your row space, then that dimension can't exceed the dimension of either Rm or Rn, the spaces that these are subspaces for. So that's what this is saying. The MIN here stands for minimum. This is a notation that shows up a lot in more advanced classes. It just means the minimum of any value, or the minimum of all the values in the set that's contained here. But I want to talk about this dimension theorem. So I basically just talked you through this proof, but with a specific example. So I'm not going to go through it again, but the dimension theorem, again, it just says that if you have an m by n matrix A, then the rank of A plus the nullity of A is n. The rank plus the nullity is equal to the number of columns. That's what that says. Okay, so you can read through the proof for a little bit more of a formal treatment, but we saw exactly why this would be the case in that previous example. This is an extremely useful theorem that we're going to see used in a couple of different ways. Let's look at a couple of examples here where this is used. So this one, find the number of parameters in the general solution of this linear system. Notice I'm not giving you the matrix A anywhere, so we can't solve this explicitly, but all we know is that A is an 8 by 10 matrix and it has a rank of 4. Well, according to my rank nullity theorem, or my, sorry, that's another name for this, the dimension theorem, the rank of this matrix plus the nullity of this matrix has to equal 10, the number of columns that this matrix has. So I can find the nullity immediately from that. The nullity of A would be the number of columns minus the rank, which is 4. 10 minus 4, that's 6. Okay, the nullity is 6. And based on our previous discussion, the nullity is exactly the same as the number of free variables in our linear system, which would correspond to the number of parameters that we need for the solution to this linear system. So the answer is just 6. Notice we got there really quickly and we didn't have to do any Gauss-Jordan, anything like that. We can just use the dimension theorem to get there really fast. Here's another example where we do something very similar. So it says find the rank of a 7 by 6 matrix A for which AX equals 0 has a 3-dimensional solution space. So don't get too caught up in the terminology here. The solution space of this system would be the nullity, or sorry, would be the null space of A, because this is a homogeneous linear system. So to say that we have a 3-dimensional solution space means that the nullity of A equals 3. So if I want the rank of A, then according to my rank nullity, or sorry, my dimension theorem, I just want the nullity and the rank to add up to 6. That's the number of columns. So 6 minus the 3 that I have for my nullity says that my rank would also be 3. Okay? Really useful theorem. Last thing for this video that I want to talk about is this next theorem here. So this theorem says that if AX equals B is a consistent linear system with M equations and N unknowns, and if A has a rank of R, then the general solution to the system has N minus R parameters. And again, this should follow from our dimension theorem, but just to quickly look at the proof, this is going to utilize a result from 4.8 that we talked about. So again, let A be a matrix where the rank is R, and because we're assuming that this is a consistent linear system, there is a guarantee that we can find a solution. X naught is going to be my particular solution that I'm singling out. But in this case, it's going to be a particular solution to the, that's a mistake. That should be B right there. A particular solution to that system. Okay, then according to the dimension theorem, the nullity of A should equal N minus R. Now, why is that? Well, again, if I wanted to find the nullity, it's the the nullity of A would be the sorry, I'm getting ahead of myself. This just follows immediately from the dimension theorem, N minus R. Okay, so now let's suppose that we have a basis for our null space? Well, there should be n minus r vectors in that basis, because that's what the dimension of that null space should be. So from that result in the previous section where we talked about how to get a general solution to this linear system here, the general solution looks like a particular solution to the system plus any linear combination that we can create out of the basis vectors for our null space. So this for any scalars c1 through cn minus r, that forms the entire set of solutions to this linear system. But if these could be any real numbers, these c's, then that just means that these c's are acting as parameters for the solution to this linear system. So because there's n minus r of those in total, that wraps this proof up. There's n minus r parameters for the general solution to this linear system.